Okay, okay. Shit. Okay, okay. Oh my god. Tengah sedap layan eh. Okay, okay, we'll wait for the others to enter. Hello, are you there? Okay, okay, dengan. Ya Allah, tadi masalah bila. Okay, okay, okay. Tak ada homework, tak ada homework. Pada ni. Okay, so can we continue? Tadi macam ramai tu, 30. Tadi aku nampak macam 30 orang ke. Dahsyat. Ya, mana? Control. Oh. Oh. Sekejap. Uh, Okay, aku rasa dah okay ke? Okay, kita sambung eh. Okay. So, clear tak? Dengar suara tak? Cakap yes. Okay. So, sambung step 3 tadi. So, step 3, calculate the expected number of pi, which is k. So, this is where the Buckingham pi theorem comes in, which is k equals to n minus j. So, what is k, what is n, what is j? K is the expected number of pi, n is the number of parameters, j is the reduction number. So, how do we want to know what is j? So, j is equals to 3 if MLT are present, which is the three primary dimensions. J is equals to 2 if only two of the primary dimensions is there. So, tadi kan kita kan tengok n equals to 7. So all of the parameters have MLT, which is the three primary dimensions. So the k is equals the n is equals to 7, j equals to 3. So 7 minus 3 is 4. So in the end we need to find 4 parameters. Okay. So what the Buckingham Pi theorem also states that if we cannot find k, which is if k is equals to 0, we need to reduce the j by 1 so that the k would be equals to 1. For let's say we have n equals to 3, the j is also equals to 3. So 3 minus 3 is 0, so we cannot find k. Okay, so now step 4, which is choose j repeating parameters. K repeating parameters. Oh shit. Wait, hold up. Okay, I think you guys should correctkan balik tadi tu. Choose k repeating parameters. So there are betul lah. J repeating parameters. Non-dimensional parameters tu yang J. Betul-betul. Total tu betul. Aku nervous. So there should be 3 repeating parameters. If the j is equals to 2, there will be only 2 repeating parameters. So how we want to choose the parameters is that you guys go look at your textbook. Okay, page berapa ni? Sekejap ni. The page 340. Okay, 340. So, okay, kita write sama-sama. So, what I can conclude from there is, firstly, the repeating parameters, this one, repeating parameters cannot be equal with the dependent parameter. That's number one. Number two, and then from there, we must make sure all of the parameters, all of the repeating parameters include MLT, or all of the primary dimensions. You cannot have 3 primary dimensions, but all of the repeating parameters only have L or T. Make sure that all of them, not macam mana? Make sure collectively they have MLT. Okay, for example, we are choosing the velocity, we are choosing the density, and also we are choosing the characteristic length. Characteristic length is L. Velocity is length over time squared. There's also time. And then there's density, which is mass over volume. So there's mass, there's length, there's time. So that is complete. Okay. So the repeating variables, the repeating parameters need to complete all of the primary dimensions. Okay. So, and also, how we want to choose repeating parameters is that we need to use the dependent parameter as our clue. So for example, they give us leaf force kan? Okay, so leaf force is the dependent parameter. That dependent parameter must exist in the list of the non-dimensional parameters, which is on page 315. Okay, so this one, okay, all of this have one or two dependent parameters. So one of the dependent parameters cannot become the repeating parameters. So clearly, our dependent parameter is force leaf kan, so that cannot be the repeating parameters. Okay, and then we construct the non-dimensional parameters. Okay, but before that, I have like summarized which non-dimensional parameters that we already learned, so that you guys don't need to worry about the other parameters, which is Reynolds number is always, because when there's internal flow and anything to do with the dynamics of a motion, there's Reynolds number. Then we have aerodynamics, pressure, drag and lift, and also fluid flow. The Mach number, Fock number, Weber number, and friction factor. Okay, so that is how we choose the repeating parameters. Repeating parameter cannot be the dependent parameter. Make sure all of the repeating parameters collectively have MLT. Okay, and also refer to the coefficients or the non-dimensional parameter list in the textbook. Okay, so now we move on to step 5, which is construct the non-dimensional parameter. So uh, so the only the repeating parameters have the power of a, b, c. The non-repeating parameters is only the power of 1. Okay, make sure you get that. Okay, only repeating parameter have a, b, c powers. The non-repeating only power of 1. Okay, so that's how you start your that's how you construct your non-dimensional parameters. So let's say we have force lift, which is our first pi must be the dependent parameter, which is the force lift. And then we put our 3 selected repeating parameters, which is the velocity, characteristic length, and also density. Okay, and then we list out we start with the primary. Okay, so according to my notes, you guys should list, like, expand the dimensions of the parameters. For example, the force is ml over t squared, the velocity is l over t, length is l, density is m over l cube. Okay, so from there you guys want to susun m l t l t l m l, and then you put the power here is supposed to be 1 and then a b c. Okay, so how I do it is start with the primary dimension that appears least in the equation. So I choose m m m m sorry, m, not the color, maybe this one, m, because m only appears twice in this equation. So m is power of 1 and also power of c. So what we want to achieve is m power of 0. So how do you want to achieve m power of 0? M needs this, the m from the force needs to multiply with the m from the density, which is m power of c. So is 0 equals to 1 plus c, because m power of 0 is equals to m times m power of c. Okay, that is like basic exponent equation. So you just solve that and find for c. Okay, I think that's all. So once you find c, you can easily find the others, which is let's pick t. Okay, t also appears only twice in this parameter. So there's t negative 2 and also t negative a. Okay, so over here, as you can see, t negative 2 and t negative a. So a is equals to negative 2. Okay, now we have a and now we have c, and then find for b, which will be equals to negative 2 also. Okay, and then when you finally construct all of 4 of your non parameters, you can relate, like, how the independent parameters affect the dependent parameter. Okay, for example, okay, there's also one more thing I should mention is that ABC can also be equals to 0. Okay, dia macam it's like this. If you have ABC equals to 0, the non-dimensional non-repeating parameter will only be equals to, like, okay, I think I should explain this. Okay, so that is A, which is angle of attack. Like we said, the non-repeating parameter only power of 1, and then the other three parameters, which is B, and also L, and also A, B, C. Okay, if that non-repeating parameter is alpha, ABC would be like not useless, but we don't need them. So A equals to 0, B equal to 0, C equal to 0. So we will only be left with the non-repeating parameter itself, which is uh, angle of attack. So that makes sense. So one more thing is the third one, which is C. Okay, C is the, okay. Let me scroll up here. Okay, let me highlight which one is the non-repeating and the repeating one. So what we choose as the repeating is the velocity, the length, and also the density. So the non-repeating is FL, alpha, viscosity, and also C. Kan tadi I have mentioned that the clues of the non-repeating parameters can be found in the table. So FL, you should find coefficient of lift. With viscosity, you should find Reynolds number. Angle of attack is already a non-dimensional parameter itself. C is the speed of sound. So how do you want to, what is the non-dimensional parameter for speed of sound? Is the Mach number. Okay, so macam you guys might be asking, in the Mach number there's no mass, there's no mass kan. Okay, wait, let me show you. V, A, then we have L, which is also V, then we have C. Okay, so C is meter over meter over time. V is also meter over time. L is meter. Rho is meter over meter. I'm sorry. This is mass. L over T. L over T. L. This is mass. Okay. This is mass over Q. Okay. A, B, C. So B and C will be equal to 0. A will be equals to 1. So A will be equals to -1. So you get C will be, which is the Mach number. Okay, so that is something new I learned, which is the ABC can be equal to 0. Okay, so that's all for the non-dimensional analysis. So is there any question from the chat? Do you want me to repeat anything? You guys faham tak? Cakap faham. How to convert non-dimensional to dimensional? How to convert? Try buat soalan. Okay. Tutorial chapter 7. Okay. Okay, so is everyone okay if we try a question? Okay, can. Okay. So a stirrer is used to mix chemicals in a large tank. Do you guys want this? I think you guys can write it. And later I share the note. Okay, so if we read the question together, the stirrer is used to mix chemicals in a large tank. Shaft power. Okay, we have the first one, which is W. First one. We have the diameter. Second one. We have density. Third one. Viscosity. Fourth one. Angular velocity is the fifth. Okay, generate dimensionless relationship between these parameters. Okay, so there are five parameters in this condition. Is the shaft power, the diameter, liquid density, viscosity, and angular velocity. Okay, so now we want to identify which one is dependent and which one is the independent. Okay, so from here, which one do you guys think is the uh, dependent parameters? Okay. Cuba teka mana satu dependent parameter. NP is over. Okay. Okay. Cepat cakap dalam chat. Say in the chat which one do you think is the dependent parameter? Tengahkan. Shaft D. Shaft power. Okay. Okay. So well done. The correct answer is shaft power. The diameter, the diameter, the density, and angular velocity is the repeating parameters. Okay. Thank you, JJ. But okay, we'll go step by step. But for now, we can identify that the shaft power. Oh, the shaft power is the dependent. The others are independent. Okay, so now you want to generate a function where W is the function of the others. Yes, this one. So once you find the dependent parameter, you want to write this equation, which is W, which is W dot, which is shaft power, is a function of diameter, density, viscosity, and velocity. Okay. So now we go to step 2. Step 2. List the primary dimensions of each parameter. Okay, let's list down all the primary dimensions of the parameter. Oh, okay, we already did that here. So shaft power is ml squared over t cubed. How I know this? How? Let me figure out. L over t over t m over t. Oh, shaft power is force over time. Okay, remember I said that we need to memorize force. Okay, what is force? Force is mass times length over time squared. So power shaft power shaft power work. Okay, power is work over time, which is also force times the distance over time. So from there, we take here, paste it here, times length over time. So we will get m power of 1 length power of 2 time power of negative 3. Okay, so that is why it is important to memorize the force. Okay, so okay, this is how I get the shaft work punya dimensions. Okay, so diameter is L, liquid density is m over L cube, viscosity is this also a file, which is m over L T. Angular velocity is also velocity. Angular is just the characteristics of it in a circular dimension. Okay, so that is step 2. We need to write down MLT and all of that. Okay, now step 3, calculate K, the expected number of pi's. So our n is 5 and there is MLT. So the primary dimension that exists is 3. There's M, L, and T. So the j is equals to 3. So n minus j is 2. So there will be only 2 pi. Pi 1 and pi 2. Pi 1 is the dependent function. Pi 2 is the other one. The other one. Okay. So from here, okay, now we enter how do we choose the repeating parameters. Okay, firstly, we cannot choose the dependent parameter. Secondly, we need to make sure all of the repeating parameters include MLT. And also one thing is that the repeating parameter cannot be complicated. What I mean is, this is a very complicated dimension. It will be hard for us to find the ABC of the power of the repeating parameters. So we want to find the simple dimensions, which is so that eliminates shaft power. And also shaft power is also the dependent. So that leaves us with 4 other parameters. Okay. So okay, let's write down. Okay, how to choose repeating parameters. Number 1, not the dependent, which is W. Number 2, cannot be, make sure all of the parameters include MLT. Okay. Okay. We can also see that viscosity is also a complicated dimension. So we cannot choose viscosity because it will be hard for us to find ABC. Okay, so that leaves us with the simple dimensions, diameter, liquid density, and also angular velocity. Okay, so does all of the three satisfy all of the primary dimension? Yes, because there's M, there's T, and there's also L. Okay, so we choose angular velocity. We also choose length, diameter, my bad. Diameter, and also diameter, and also density. Density. Okay. So okay, that is step 4. Now step 5, construct the non-dimensional parameters. Okay, so start here. We start with, I started with pi1 for viscosity, because this will be equals to Reynolds number, but never mind. We start with the sharp power, which is the dependent one. The dependent must be pi1. Okay. So okay, as we said, we need to list down all the dimension here. We need to find MO, LO, TO. Okay, so okay, kita buat yang tadi tu. Which one appears the least? M, O, M only twice. T pun 2 kali je. L 3 kali. So we would start with M or T. We cannot start with L. Okay, so from M, 1 A, and that's all. 1 plus A. So A equals to negative 1. Then we start with T. T is negative 3. Negative 3. Negative 3A. Yes. Negative 3A minus B. Negative 3A ni. Betul-betul negative 3. Okay. So negative 3 from here, and also from here negative B. So B is equal to negative 3. Then L 2, 2 tolak 3A tambah C. Okay. 2 tambah 3A tambah C. M, okay, let's just write it here. 2 tolak negatif 3A negatif 3A tambah 1 C. Okay, because A is negative 1, so that makes 2 plus 3 plus C. C go over there, so it's negative 5. So in the end, we have this. Oh my god. Okay. Okay, this is in here. Okay, so from there we can find the power number NE. Okay, so kan tadi saya cakap the dependent parameter should be appearing in the list of non-dimensional parameters. So if you go to page ni page 316, power number, ada power number. So dia ada W kat atas tu, and then row D kuasa 5, angular velocity kuasa 3. So dah dapat dah power number. Okay, then this one pula, this one is Reynolds number. Okay, so this one quite easy. So okay, that's the first question. I mean, not the first question, I think that's the only question you need to do. That's the just proof this one. Okay. Okay, so can we move on to chapter 8? Is everyone clear with chapter 7? Say in the chat. Yeah, go. Clear. Okay, chapter 8 banyak. Okay, so now we go to not my least favorite lah, but it's actually quite interesting. There is a lot to cover. So okay, let's take 5. Take 5. This is a long chapter. Okay, okay. Then, yes, I think it's better kind of stop this page. Okay, hold on. Anak menteri. Share this also. You know how much pages chapter 8 has? It's like they got like 113 pages, bro. Okay, so I think that's 5 minutes. So okay, I think everyone can get ready. So this is chapter 8, internal flow. Hello, I sound like Dr. Pooh, bro. Okay, everyone here? Everyone ready? Everyone ready? until like a whole level. The audio stream current bitrate is 0. Hello, dengar tak? Dah hilang ke? Mana korang ni? Ya, okay. So, okay, Bashir je ada. Lain-lain. Mana ni? Faris, Afif, Fadil, JJ, sebagai Ashraf, Anas. Masih ada ke? Ada. Okay. So now is internal flow. Ivan, Ashraf, Aidil, Afif. I am Anas. Okay. Thank you for joining my live stream. Okay. So let's start chapter 8. Internal flow. So what is internal flow? Internal flow is basically fluids that is flowing in a closed volume ataupun the fluid flowing in the space is is filled with the fluid. Maksudnya pipe tu tak ada udara, or pipe tu tak ada, sorry, in the pipe there's only one type of fluid. Okay, that's the internal flow that we are learning right now. There's only one type of fluid in the closed pipe. Okay, it's either gas or it's either liquid. Okay, so laminar and turbulent flow. Laminar is small streamline. Okay, I'll show it. Okay, let's go with green. Okay. Smooth, streamlined, and highly ordered motion. Laminar. Turbulent is velocity fluctuations and highly disordered motion. Transitional flow is the flow that fluctuates between laminar and turbulent. Okay, so when we mention about turbulent, we need to mention about velocity fluctuations. Okay, why we need to mention about velocity fluctuations is because when the flow is turbulent, there are some parts of the region that move slower than other part of the region, and it is inconsistent. So that is what we call the velocity fluctuations. It is inconsistent velocity at different regions at different time. Okay, that is turbulent. Laminar is smooth, streamlined, and highly ordered motion, whereas turbulent is highly disordered. Like I said, it is inconsistent and it moves and it different in time. Okay, so let's talk about the Reynolds number. Okay, oh my god, this is gonna be so long. Okay. Reynolds number is the ratio of inertial forces over the viscous forces. So what does that mean? Inertial forces is basically the force that makes the fluid go or makes the fluid move. You know, like you have a bottle kan, and then you guys goncang. Okay, most of the energy is inertial forces. You move the fluid. Viscous forces is the force that restricts the flow of the flow of the fluid basically. So initial forces is how the fluid moves and what makes it move. Viscous forces is the force that wants to limit that motion. So Reynolds number is a perfect dimension or a perfect situation for us to like determine the ratio of these both forces. So okay, let's see here. So Reynolds number is V average times D times I think I should use this. Velocity, average velocity times the diameter of the pipe times the diameter of the pipe or the characteristic diameter if it is non-circular. Rho is the density of the fluid. Mu is viscosity. Mu over rho is also equals to this weird V shape, which is also called the kinetic viscosity. Okay, so the initial forces, which is the top part that makes the fluid move, is this symbol means directly proportional to fluid density and also fluid velocity. Okay, so okay, uh, I hope you guys can like zoom into my PDF because the notes are really compact, so you guys really need to zoom in. So that's the difference between a large Reynolds number and a small Reynolds number. A large Reynolds number means that the ratio is too large relative to the viscous forces. Okay, talking about the ratio, kan? If you have a very high ratio, it means that the inertial forces is very high and the viscous forces is very low. Okay, so when you have a large Reynolds number, the viscous force cannot prevent the random and rapid fluctuations of the velocity of the fluid. Like I mentioned, the initial forces is what makes the fluid move. If the viscous forces that restricts the motion is very small, in comparison to the initial forces, then the velocity will be fluctuating and it cannot be controlled. So that is why large Reynolds number have a turbulent characteristics. So we move on to this. In comparison to the small Reynolds number, the small Reynolds number, the viscous force are large enough to suppress the fluctuations and keep the fluid in a laminar motion or control motion. So we have a low Reynolds number. It means that we have a low initial force and very high viscous forces. Okay, so there is a fine line between small Reynolds number. There's a fine line between laminar and turbulent characteristics of a fluid. That's why I put this dotted line. So this dotted line is called the critical Reynolds number. So if you go below the critical Reynolds number, you will become laminar. Lower Reynolds number usually is laminar. If you go higher than the critical Reynolds number, it will become turbulent. Okay, so that's the principle behind it. So what is how do we know what is the critical Reynolds number? It is where flow becomes turbulent from laminar and where values differ according to the geometry and flow conditions. This is where we enter the pipe geometry. Okay, as we said, the Reynolds number depends on D. So what is the D? The divine, tak ada lah. The D tu is the geometry of the pipe, whether it's circular or non-circular. So if it's circular, it would be just D equals to the diameter of the pipe. So the critical Reynolds number for a circular pipe is 4,000. In the textbook, there's also like a conflict is whether it's 4,000 or 10,000. But hari tu I asked doctor, doctor said 4,000. So we use 4,000. Okay. Oh, okay. So as you can see here, okay. So below 2,300 is laminar, below 4,000 is transitional, and above 4,000 is turbulent. Okay. So that is for circular pipe. What about non-circular pipe? Non-circular pipe or ducts for transporting gases. It is uncommon for you to transport liquid in in like a square shape or rectangle shape unless it's like an open channel. It is always the square ducts and rectangular duct is always used for transporting gases because it is much more easier to construct the ventilation. Ventilation. Okay, so kan I cakap tadi what is the D? The D is the hydraulic diameter or the characteristic diameter. So how do you want to find it? This is actually in the textbooks. The primary formula is 4 times the area over perimeter, 4 AC over P. So that's the channel, square dot, and rectangular dot. Okay, you guys can see the textbooks. And then we move on to the next one, which is the entrance region. Okay, there is a lot of terms that you actually need to understand to identify the entrance region. Okay, so I have listed down all of here, also that highlighted the important things. Okay, let's read it one by one. Okay, so first is the velocity boundary layer. Is the region of the flow in which the effect of viscous shearing forces caused by the fluid viscosity. The that one is over here. Okay, that is the velocity boundary layer. The boundary layer region is the viscous effect and velocity change are significant. Okay, what does significant mean? Significant means the change will be big. Insignificant means the change will be small and it will not contribute changing the overall equation. But if it's significant, it means that uh, it plays a big role. Macam, okay, let me see. Where is the boundary boundary layer region? Boundary layer region is from here to here. Okay, this is the boundary layer region. Okay, as you can see in the boundary layer region, the velocity profile, I think I should show. Okay, this one. Okay, the velocity profile is like that. There is like a linear gradient. So that linear gradient is what we call the effects of viscous. That is the viscous effects, the linear gradient. Okay. So number 3 is the irrotational flow region. So what it means is if you observe the pipe from in front like that, the what we assume is that there will be no the liquid will not be swirling. The liquid will not be swirling around in a radial direction. So the frictional effects are negligible and velocity remains constant. The velocity remains constant in the radial direction. So we assume that the flow just like that. Dia tak pusing-pusing-pusing. Macam tu lah. I don't know if you guys understand or not. Tapi okay, let's move on. The hydrodynamic entrance region is the region from the pipe inlet to the point where which the boundary layer merges to the center line, which is the hydronic. Okay, this one. Let's take red, orange. Hydrodynamic entrance region is the region before the so before the fully developed. This is fully developed. Fully developed. Entrance region not equals to the fully developed. Cakap hai. Ni ada 21 orang tengok. Uish. Okay. Bye. So number 5 is hydrodynamically developing flow. The point of the velocity profile develops. This is the point. I mean this one. This one is the point. Developing flow. Okay, number 6 is hydrodynamically fully developed region, which is this one. Okay, region is like area, something like that. So this region here is the entrance region. This region here is the fully developed region. Okay. Hydrodynamic entry length is the length of the region itself. That is actually quite straightforward. So this is the formula for laminar and turbulent entry length. Okay. So there is an assumption. We need to make assumption. The pipes are several times length of the entrance region. The flow through the pipes is fully developed for the entire length of the pipe. Okay, why do we need to assume this? Is because if the pipe is shorter than the entrance region, it will not fully develop. You see, what we are assuming right now is that the pipe is longer. What we don't want to assume is the pipe is shorter than the hydrodynamic entrance region. So the pipe needs to be longer. Okay, so if it's longer, there is much more area the fluid is fully developed. Okay, that is the first one. The second one is it is fully developed for the entire length of the pipe. What it means is there is no obstruction in front of the pipe. Okay, so that is one of the assumption for the entrance region. Okay, now we go to the laminar flow in pipes. So let's start with pressure drop. So pressure drop is due to the viscous effects representing an irreversible pressure loss. Okay, so this is like something I would like to share. Viscous is internal friction of a fluid. Okay, so in real life, if you have friction, like between your hands and the mouse, the friction will generate heat. Okay, heat is an irreversible energy. Once lost, you cannot retrieve. That is what we call irreversible. So imagine the fluid has friction between each other. So that friction generates heat also. So viscosity generates generates friction, which also generates irreversible heat. Okay, so from there we can assume that the viscous effects represent the irreversible pressure loss, which is the energy uh, it, it is the heat energy produced by the friction. Okay, let me just make that into a word. Energy released as heat from the friction. Okay, so that is where the energy is lost through the viscous effects. So now we understand what does pressure drop mean. It means due to the viscous effects that represent irreversible pressure loss. So now we have a lot of okay, where do I start? I think I should start here. Okay, pressure drop. Yes. What is pressure drop? Mathematically, is pressure at one point is different from another point. So the pressure drop means that the final pressure is lower than the initial pressure. Okay. So from there, we can make an equation P2 minus P1 over L is also equals to the change in pressure dP over dx, which is with respect to the length of pipe. Why do we want to relate this with the length of the pipe? It's because the viscous effects comes from the surface of the pipe, and also, okay, if you have laminar flow, this is what we call the no slip condition. Oh my god, no slip condition. Okay, so from that no slip condition, it generates shear force. So that is why the length of the pipe is important to find the pressure drop. Okay, So pressure drop is the change in pressure with respect to the length of the pipe. Okay. So now we have this is a formula. You guys can look in the, where is it? Chapter 8, the task. We do manifold pipes. Okay. This one. So I cannot really understand like why is it so like bersepah kan. So I clean it up. I clean it up for you guys. So over here we have laminar and turbulent. Laminar formula has a different formula from the turbulent formula. That is important because if we answer the, okay, over here, if we assume for the flow to be laminar, we use the laminar equations, we use the laminar formulas, the output will be different, very different from the, if we would assume it to be turbulent. Okay, that here, if it's turbulent we need to use very specified formulas. Okay, so that's why I pick, there's a difference between turbulent and laminar. Okay, so for the laminar, pressure drop P1 minus P2 is equals to 32 viscosity times the length of the pipe times the average velocity over d squared. Okay, for the turbulent or all types of flow, including transitional flow, the pressure drop is equals to the friction factor times L over D times density times average velocity squared over 2. Okay, so as you can see here, the pressure drop in laminar tak ada F, tak ada friction factor. The pressure drop in turbulent has F or friction factor. So this shows that friction is a function of Reynolds number for laminar and is independent of the roughness of the surface. The pressure drop for a laminar flow is independent of the friction factor, whereas the turbulent is dependent on the friction factor because there is F in the formula. Okay, so how do we find F? If we want to find F for the laminar, it's 64 over Reynolds number. If we want to find F for the turbulent, is 8 times the shear stress of the surface wall over rho V squared average. This is also called the Darcy friction factor. It's in the textbook. But okay, just so you know, it is all type of flow. This is laminar. So okay, so okay, you guys might be wondering, like there's only one variable in the friction factor, which is Reynolds number, and also here. So this one is actually a very linear graph. If you can see the Moody chart. Later we will go to the Moody chart, but for now, this is the formula. Okay, so we are talking about laminar flow. So from the laminar formula, we will use it in finding the flow rate. V dot is flow rate, V average is velocity. You guys cannot mix that up. V dot is flow rate, V average is the velocity. So this is one guy, I don't know how to pronounce his name, Poissier's law. He's a French physicist. Okay, so this French physicist used the laminar formula to find the flow rate. So what he comes up is with the area, the cross-sectional area times the velocity average is equals to this. Pressure drop by the 0.4 viscosity times L. Okay, so this is how you derive it. Okay, so in the question, they would in the question usually the flow rate will be given, but we want to find the pressure drop. Okay, so how do we want to find the pressure drop? We find delta P. So we just rearrange the Poiseuille's law. So as you can observe in the formula here, the pressure drop is directly proportional to the length, inversely proportional to the diameter, and also directly proportional to the viscosity. So if you guys want to decrease the pressure drop, you guys should increase the diameter. If you guys want to macam tu lah, the higher the if you guys want lower pressure drop, you guys should uh, make the diameter bigger. If you guys want a lower pressure drop, you need to make the viscosity lower. Pressure drop, we need to make the length shorter. Okay, macam tu. So that is how the equation works lah. Okay, so now we have the effect of gravity. So this is when the pipe is on an incline or angle. So just memorize this. It's already in the book. So just masukkan the data. So this is the velocity profile for a laminar flow. The velocity profile is the graphical method to find the velocity at one point using the radius. Okay. So we assume it to be a quadratic equation. It looks like a quadratic equation, right? Yeah. So that is what we call the velocity profile, or the function of the velocity at a certain point from the radius. Okay. So the maximum velocity is 2 times the v average. That is from this derivation, chapter 8. From atas ni, jadi derivation. So derivation tu kat tak risau. So for the assumption for laminar flow, consider it steady, laminar and incompressible, and also fully developed. Macam tadi lah. Head loss is represented the additional height that the fluid needs to be raised by a pump in order to overcome the frictional losses in pipe. Head loss is also equivalent to the pressure drop, but it has a different dimension, which is meter. Why people want to use head loss is because they have a much simpler dimension. For example, how much head loss does one system has? So they say 40 meters. So you would senang lah nak fikir, oh 40 meters head loss. So all you need to do is insert a pump that has a higher head pressure. If we want to like pressure drop, people would just like how much pressure drop for that system is like 30 kilopascal. So you don't know how much pressure drop it actually is, because you don't know the dimension of the system and all. So head loss is used because it is much more simpler than pressure. Macam tu lah. Because it already includes the density and also gravity. So it's a simplified pressure drop. Okay. So now we move on to turbulent flow. Turbulent flow. Okay. So ni aku buat nota tadi. Okay. Before that, does anyone wants to ask about laminar flow? Does anyone wants to ask anything from the first page? Please stay in chat. Any question? First page. Clear. Okay. Okay, turbulent flow. I hope you guys are still okay. Thank you for tuning in. I am very, very, very honored to share knowledge with you guys at this late night. Tak apa, kita stay up sampai tengok World Cup. Okay, so resuming. Turbulent flow is characterized by a disorderly and rapid fluctuation of slowing regions of fluid, called eddies. So it is, as I said, turbulence is when there are inconsistent fluctuations of velocity in certain regions. Some regions has lower velocity than other regions and it is inconsistent. So what do we call this inconsistency? Is we call it eddies. Eddies. Okay, okay, eddies. I need to highlight this. Characterize swirling fluctuation of flowing regions of fluid. Okay. So how does eddies affect the flow? Eddies can transform mass, momentum, and energy. Why does it say it can transform mass? Because it can make one region less pressure than the other region. So the density would be different. That is one. Momentum is mass times velocity. So if the mass is different, the velocity would be also different. So that is change in momentum. Energy is energy. So some in a turbulent flow, some energy is lost and some energy is regained. So that is the effects of eddies. So the effects values of friction, the higher, well, okay, higher values. Oh, okay. So the addition of eddies in the flow would raise the friction, internal friction, the heat transfer, and also the mass transfer, because the fluid acts differently and is unstable. Okay, so that's the basic principle of turbulent flow. Okay, now we have turbulent shear stress. Internal flow shear stress is tau total is equals to tau laminar plus tau turbulent. So this is the turbulent component. This is the laminar component. We want to find the turbulent component, which is also equals to negative rho u prime v prime. Okay, so this formula is also called Reynolds stresses. Okay, so the turbulent component is also can be represented by mu t du over dy. Okay, so what is mu t? Mu t is the kinematic viscosity lah for the eddy current or the turbulent current. V or mu biasa lah, mu biasa is what we call molecular diffusivity of momentum. It's a fluid property. Okay, this doesn't make sense much. Aku tak faham sangat, tapi tak apa. Ada dalam buku teks lah, so kita just go with the flow. So, oh no, this is not kinematic. This is just a regular. Okay, that makes sense. So mu is like a normal viscosity. The weird V shape is the kinematic viscosity. Okay, viscosity over rho over density is the kinematic viscosity. So this is the T here represents turbulent or the eddy diffusivity. It is not a fluid property. It is dependent on the flow. Okay. This is two different points. Okay, so you guys might be asking, what is du over dy? Du over dy is the gradient of the velocity profile over here. So this is the internal force shear stress equation. So we expand it, and then this is tau total equals to the laminar component plus the turbulent component, which is the mu t. This mu is the regular mu you use, which is the mu yang biasa tu lah, yang kat atas tu. Okay, so we need to add the both components, and then both of them is also has the velocity gradient. Sini, this is called the velocity gradient. Okay, so as you can see here, the velocity gradient for the laminar flow is higher than the turbulent flow. You know why? Because uh, because of this. Okay, now we enter to the next one. Why is the laminar flow gradient much higher than the turbulent flow? Okay, it's because it has a thinner viscous sublayer. Okay, so turbulent velocity profile. So there are four categories of the velocity profile, which is the turbulent layer, the overlap transitional layer or the inertial sublayer, as you can see here, the buffer layer, also the viscous sublayer or the linear, laminar or wall sublayer. Okay. Okay. So as you can see here, like we mentioned in the first page, if you have a large Reynolds number, the inertial forces is much bigger compared to the viscous forces. This translates to the velocity profile. So the viscous sublayer is very thin compared to the turbulent layer, which is the initial forces. So that's how we get it. That is the characteristics of a turbulent flow. So this turbulent flow is a fully developed turbulent flow. So fully developed doesn't mean it's laminar. Fully developed means the velocity profile is constant from one point to one point. Okay, so it is constantly at the same velocity profile. So you can have a fully developed turbulent flow, you can have a fully developed laminar flow. As long as the velocity profile is constant from from one point to one point, that is what we call a fully developed region. Okay, so now we proceed to the Colebrook equation. Okay. So the Colebrook equation is used to find the friction factor. Friction factor. So this is the equation. What you guys need to remember is it has certain parameters that we need to key in to find, which is the relative roughness and the Reynolds number. The others are just constants. Okay. So how we want to find the relative roughness is, if you open your textbook, is page 368. They will show you the roughness. For the Reynolds number, you need to calculate yourself. Okay, so from the Colebrook equation, we can have an implicit approximation. What does implicit means? It means that there are two uh, dependent variables in the equation. So there's one f here and one f here. It's like very hard to solve. So how do we want to make it simple? By making only one dependent variable in front on the left hand side. On the right hand side, there is no f. So it is much simple and we can say it as an implicit approximation. So what is this implicit approximation name? It is called the explicit Hallan equation. So the explicit Hallan equation only has the also have the same variable, which is the relative roughness and the Reynolds number, but there is no friction factor. So this is much more easier to solve. So if in a question you are asked to find the friction factor, you guys can both use the Colebrook equation and also the Hallan equation. But you need to mention that the Hallan equation is an approximation. It is not totally accurate. Okay. So as you can see here, both of these equations are for smooth and rough pipes. What happens if we have a smooth pipe? As you can see here, a smooth pipe has a zero roughness. So if it's zero, we can eliminate this. We can eliminate the formula here and simplify it. So E equal to 0, and then 2.51 is a constant, so we can eliminate that also. Since Reynolds number over square root of friction factor is a power of -1, we can like eliminate this. How should I explain this? You see here, kat depan ni ada negative 2 kan, tapi sekarang dah tak ada negatif, dia jadi positif. Sebab dia naikkan Reynolds number kali square root of friction factor tu. So this is the equation, this is the formula for a smooth pipe. So it's just 2 ln bracket Reynolds number friction factor square root of friction factor minus 8. This is what we call the Pareto equation. So Pareto equation is for smooth pipes only, where the epsilon is equal to 0. Okay, so that is the how we find the friction factor. Okay, now we move on to Moody chart. Moody chart is another way to find the friction factor. So how do you find the friction factor? Okay, let's go. Where is the Moody chart? Here. I see. Reynolds number. Okay. So how do we use this chart? You might ask. So first, you guys need to find the roughness, the relative roughness. Secondly, you guys need to find your Reynolds number. From there, you can follow the line. Okay, let's say our roughness is 0.0002 and our Reynolds number is 10 to the power of 5. So we follow this line here, and see where it intersects with the. I don't think I should use red. I think I should use green. Okay, nampak sikit. Okay. So we see where it intersects. Okay. So it intersects there. So firstly, find the relative roughness. Secondly, find the Reynolds number, and then see where it intersects, and then you can plot it and find the friction factor, which is 0.025. So the Moody chart is actually very simple. So the Moody chart is also a way to verify your formula. Like you already calculated using the Colebrook equation, you need to verify using the Moody chart. So there's usually two solutions to one problem. This is the first solution. This is the second solution. Okay, so what can we observe from the Moody chart? There are three things that we can observe from the Moody chart. Firstly, at very large Reynolds number, the friction factor curves are nearly horizontal. The thickness of the viscous sublayer decreases. It is negligible compared to the E, which is the relative roughness. It is independent of Reynolds number. It is also called the fully rough turbulent flow. Okay, remember I said about the thickness of the viscous sublayer. When it has a higher Reynolds number, the viscous sublayer becomes very thin. So if it's thin, it is negligible. Is negligibly small. Okay. The curves are nearly horizontal. What does that mean? It means that it is approaching a constant value. So the higher you go in a Reynolds number, the more trend you can see that the value of the friction approaches to a constant, which is horizontal line. So that is why it is they say that's why we conclude that from a certain point the friction is independent of Reynolds number from a certain point, because the friction will be constant. So it doesn't matter if you have 10 to the power of 6 or 10 to the power of 7 Reynolds number, your friction factor will be the same. That is what they mean. Okay, so you can look at the Mugi chart at page 952. Okay, that's the first observation from the Mugi chart. The second observation is that for laminar flow, the friction factor increases while the Reynolds number decreases, and it is independent of the surface roughness. So what it means is, if you observe the laminar flow here, dia makin tinggi Reynolds number, makin rendah dasi friction factor tu. Sebab dia inversely proportional. 64 over RE is inversely. The higher the Reynolds number, the lower the friction factor. Okay. And then in the textbook, they also say that you need to make sure that you are using the actual internal diameter of the pipe. Okay, so usually what do they ask in questions? They ask the fluid flow problem. You need to find the pressure drop or the flow rate or the pipe diameter required. Okay, so this is what the questions would usually ask lah. They would ask you to find one thing given the other parameters. Okay. So is everyone still with me? Hello, are you there? Is everyone okay? Do you guys need any reflection or need me to repeat anything? Not okay. It's a lot. Faris, I ate ready. Okay, tak apa Faris. What do you want to ask Faris? Oh, banyak tu. Take 5. Okay. Uh, Ashraf suggests that we take 5. So we take 5. Come back at 1:70. Okay, we are back. Okay, guys. Say in the chat. Are you guys ready? We are back. Okay, cakap saya ready. Ataupun cakap saya okay. Banyak tu. Like honestly, aku rasa chapter 8 ni really over the top lah. Like you need to cover a lot of topics and subtopics. You need to have, sebab dia macam apa, open book test lah. So aku rasa macam okay lah. Tapi aku tak tahu nak expect soalan macam mana tu. Sebab dia open book test. So it might be hard, might be easy. So okay. Alright, so let's resume. So minor losses. So what is a minor loss? Minor losses comes from fittings. Sorry, that's my turn. Fittings, valves, bends, elbows, teeth, inlet, exit, enlargements, and contraction. What does these components do? They interrupt the smooth flow. If you interrupt the smooth flow, there will be firstly flow separation, irreversible deceleration, and also mixing of the fluid. So you guys need to remember this if it comes into the question they ask you theoretically. Where how does a valve interrupt the smooth flow? So the valve interrupts the smooth flow by flow separation, irreversible deceleration, and the mixing of fluid. Alright. So minor losses that is so there is a formula to find the loss coefficient, which is HL over V squared over 2G. V squared over 2G is the dynamic parameters. HL is the head loss due to the components. Okay, so HL is also equals to mana tadi? HL pressure drop. Sini. From here, pressure drop over rho G, korang boleh letak dalam sini. Pressure drop over rho G. Sebab G dah ada sini, dia cancel out. Okay. Hey, welcome Faris. Let's go Faris. So this is the simplified equation of the loss coefficient after replacing HL. So we can also represent minor losses by the equivalent length. What does the equivalent means? It means that if you put a component, like if you have a valve, there will be a pressure drop kan? The pressure drop will be also equals to the length of the pipe just from the normal effects of viscous. So that is what the equivalent length represents. The diameter over the friction factor times the loss of coefficient. So equivalent length. I think that's mentioned here. Minor losses. The head loss caused by a component. Wait. So this is the equivalent length if the equivalent to the pressure loss due to the component. Okay, that is simple. Okay, so right now we go to the assumption. Flow is steady. Flow is steady and incompressible. Flow is fully developed. Either it's laminar or turbulent. Okay, so there are two principles that we need to use during the calculations of the head loss, or this case minor losses, which is the conservation of mass. So conservation of mass is m dot 1 equals to m dot 2. The mass flow rate into a pipe is equals to the mass flow rate exiting the pipe. So there is also the density V1 A1 equals to the density V2 A2. Density is the same, so it's just V1 A1 equals to V2 A2. Okay, that's easy. So that's the conservation of mass. Conservation of energy is written here. So energy in this is represented by H, which is meter. Meter. We can also represent energy as meter, because energy is mass, oh, mass times length, length squared over t squared. Okay. So we can represent energy in terms of length. We can represent energy in terms of mass. Okay. So right now we are representing energy in terms of length, which is the pressure, uh, the head loss, the head pump. So we have static pressure, dynamic pressure, dynamic pressure plus G is elevation, H pump if we have a pump. This is the P2, V2, Z2, H turbine if we have turbine, and finally we have the H loss, which is the total loss. So the conservation of energy basically states that the energy in is equals to the energy out. Okay, so from here we see this HL. What is HL? HL is represented by H total, major head loss and minor head loss. So HL is equals to the okay, I don't know what does this actually means, but this is the friction factor, length, diameter, velocity squared over 2g plus the minor losses. This is the major component, this is the minor component. Okay, let's jot that down. This is the major component, this is the minor component. So if you want to find the minor losses only, use this. If you want to find the major losses only, use this. What is this? Where can we find this? We can find this from here. Ah, here. Okay. Did you see the similarities? Friction factor L over D, velocity squared over 2g. See? Same kind. See? Okay, so this is the minor losses. Where can we find this? We can find this from here. Okay. So, okay. This is the equation if the inlet is not similar to the outlet. So I is this I, and J is also the I juga. Tapi this is what they mean. Hmm. The geometry of the pipe is like this. Dia makin kecil. Okay. So this head loss is for the constant D, which is dia punya diameter, the shape of the pipe remains constant. Okay. So you use this plus this, since the velocity is the same, factorize outside and then just add the friction L over D plus the loss coefficient. Okay. This is when you have the constant D. Okay. So that is minor losses. Now we masuk piping networks and pumps. So let's talk about pumps. Pump is the mechanical energy required to increase the pressure. So when we increase the pressure, we can represent pressure in terms of head or meters. So of meter. So that meter is required. The pump supplies energy to overcome the elevation difference and also head loss. Okay. Mak. Okay. OBS aku buat hal. Like. Okay, I think there will be we will be tutup. Jangan main ni. Okay. So the head pressure generated by the pump is to overcome the elevation differences and also head loss. If there is no elevation, it will just only overcome the head loss. If there is elevation, Z2 minus Z1. Okay, that is simple. So from fluid mechanics 1, we know that the efficiency is the desired output over required input. Dr. Chu ajar. Remember? Okay, so to find if the efficiency of the pump is given, we can find either the power of the pump or the power of the power from the shaft. Okay, so this is the formula. Usually they would give us the efficiency of the pump and also the efficiency of the motor. So we just need. So this is the equation. The power of the pump over power of electric would be the efficiency of the pump motor. Okay. So macam ni. So the head generated by the pump is equals to the elevation difference plus the head loss. This is the elevation difference, Z1 and Z2, and also the head loss inside the pump. W pump is the power by the pump. Power is rho V G H. Energy times velocity times volume. Okay. So there are two. Okay, now we enter the pipes. Study pumps, now pipes. Pipes that are series and also parallel. The series pipes, the flow rate of series is like where is the series? Ini series. Okay. Serial flow and parallel flow. Serial flow, the flow rate coming inside is also equals to the flow rate coming outside. This is from the mass conservation of mass. The HL total is equals to the total of head loss from point A and also point B. Different from parallel systems. Parallel systems, the head loss from point A to point B is equals, but the flow rate will be different. Okay. So, okay, let's jot this down. Flow rate can be different. Ini head equals head constant. Ini flow rate constant. Ini head can be different. What does that mean? It means that the head here must be equals to the head here, but the head here can be different from the head here. In comparison to the flow rate, since there's only one pathway, the flow rate must be the same. But this one, the flow rate is different. Ah, because there's two different paths. All right. So this is the formula for the parallel. Oh shit. Okay, this is the formula for the parallel pipe system. Okay, I think to explain. Oh, what we have here. Oh, this is usually they will give the velocity. Okay, or we want to represent this equation in a velocity dimension. So we would exchange here. And then this is the flow rate. So usually the question would give us a flow rate and ask us to find the pressure drop or the pipe diameter required. Okay. But for the pipe systems here, we can find D1, we can find D2, we can find L1, we can find L1, we can find L2. So there's much more parameters that we need to consider. So from the equation here, we can conclude that the flow rate is directly proportional to D, inversely proportional to F, and also L. So if you want to have a higher flow rate, you need to have a bigger diameter, you need to have lower friction, and you also need to have a shorter pipe. Alright, so that is the piping networks. Now, flow rate velocity. Oh, okay, dah dekat habis dah guys. There are three types, three topics. First is the pitot tube. Pitot tube there are two different pitot tubes. Single pressure and also double pressure. That's what I call it. The single pressure just only measures the stagnation pressure. The double pressure measures two differential pressure, which is the static pressure and also the stagnation pressure. Usually, this pressure meter is used for stationary. Used for stationary devices. The differential pressure is usually used for moving devices. Alright, so this is the formula, quite simple really. Then we go to obstruction flow meters. Okay, so I just want to share how we derive this equation actually. Okay, so this is the cross-sectional area. Okay, bear with me. A2 over A1. Area is pi r squared over pi r squared. R can be also represented by diameter because diameter over 4, 4 is just another constant. So we can cancel out the 4. So the ratio of the area is also equals to the ratio of the smaller diameter over the big diameter squared. So we represent the small diameter over the big diameter with B. Okay, so that's the first simultaneous equation. Second one is the conservation of mass and also the conservation of energy. From the conservation of mass, we know that the area is also the velocity is also relates to the area. So the bigger the area, the smaller the velocity. Okay. So velocity is also so since the area ratio can be represented by the d, the ratio of the d's, we can also represent the ratio of the velocities by the d, which is b squared. So we derive and then we get this equation. Okay, so that's how you derive it. This is the shapes of the obstruction: orifice, flow nozzle, and venturi. This is the discharge coefficient, VAC, we need to find V here, CD. CD, how we want to find CD is based on the area ratio or the diameter ratio and also the Reynolds number. Okay, so flow meters ni is just in the textbooks, quite simple. There's a lot. Positive displacement, turbine flow meters, pedal wheel, variable area, ultrasonic, electromagnetic, vortex flow meter, thermal anemometers, laser Doppler, and particle image. Usually the bottom three is used for gas fluids. The others are used for liquids. So that is all from chapter 8. I think you guys deserve, for the ones still watching, I am very proud of you guys. You guys are still here. So we have completed a summary of chapter 8. Well done, guys. Well done, guys. So do you guys want to do exercise or do you guys want to take 5? Up to you. I love you guys also. Yay. Okay, so you can also do some tutorial. Laminar flow, diameter. Hey. Alright, welcome guys. So, okay, uh, you guys want to do this or want to take a break? Take break or exercise? I will share this exercise. Okay, we take 5. Talking about Velo kan, aku dah lama tu tak main Velo. Aku tak tahulah akaun aku ada. Jadi last time aku main Velo, I think I streamed the last time I play Velo. When was the last time I played Velo? Let me see. It's been a long time. I rasa 3 months ago. I think that's about it lah. The last time I've been playing 3 months ago. Dah kena ban kot. Cesar kena ban. Aku dah beli banyak skin tu. Aku ada River, ada Glitch Pop, okay, ada Prime, mahal. Kalau dah kena ban tu, tahu lah. Tapi tahu lah, aku dah move on tu game lain. Overwatch macam best. Hari tu aku main aku suka ni Bloodborne best. Aku main kat PS4 lah. Abang penyu buat apa je abang penyu? Kena ban sampai sangat. Tak ada dah. Aku rasa antara banyak kawan-kawan aku tak spend banyak sangat lah. Aku beli berapa je sekali tu. Tak banyak sangat lah. Overwatch best tu, tapi tu tak ada masa. Overwatch best. Dia kalau kau kalah, game tu sekejap je. Kalau kau kalah Velo kan, kau kena hadap tau game tu 20 minit. Aku macam lama tu. Kalau Overwatch kalah sekejap, kalau menang sekejap. So aku rasa that's a appeal lah for some gamers. Kejap je tu game tu. Okay, I think that is the end of our break. Let's do some exercise. Kita pergi share dulu. Saya nak share. Sekejap aku nak share notes. Cepatlah. Okay. There's one more. What's this one? Oh, that one is. Okay, welcome back, guys. Now we are going to do the first example. Laminar flow in horizontal and inclined pipes. Okay, bismillahirrahmanirrahim. Consider the fully developed flow of whiskey at 40 Celsius through a 7 meter long, 4 centimeter diameter horizontal circular pipe. Okay. So 40 Celsius, 7 centimeter long, 4 centimeter diameter. Horizontal means there is Z is the same. Circular pipe dh equals to d fully developed. So that is one of our assumption. If the flow velocity at the center line is measured to be 6 meter per second, that is the V maximum. Screen nasi distorted. Oh, hold on. Let me just. Is it back? Okay, it's back. Jiggle. 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 Okay. So the V max is equal to 6 meter per second. Determine the velocity profile. Velocity profile, pressure difference, and useful pumping power required to maintain this flow. Pumping power. Determine the percent increase for the flow rate if it's inclined 15 downward and 15% upward. Kat sini. So, example ni, dia dalam buku teks salah. Sebab hari tu aku share dekat buku. Okay, kita tengok chapter 8. Chapter 8. Mana? Example 1. Okay. Kat sini kan. Ni salah ni. Macam saya. Sebab apa dah? It's actually supposed to be 20% and 14%. Okay. So, let's start. Okay. So now we have temperature 40 degrees, length 70 meter, diameter is 0.4, Vmax is 6 meter per second. So from this, we assume the this is what? This is water. Glycerin. So we need to find the density and the dynamic viscosity, which is this one. Where do you find this one? Jap. This is here. Okay. Jap. Sini. Sekejap kita tengok. Sebab hari tu value tu dia bagi oleh doktor. So, search A9 kan air atmosphere gases tak ada liquid property of liquid ada ke A7 siapa tahu macam mana nak cari dia punya viscosity dia temperature 40 okay so you guys go to page 954 dekat sini ada glycerin. Okay, just 9 5 it's right. 954. Okay, everyone go to page 954 in your textbooks. Ada glycerin for temperature 40 degrees. The density would be equals to 125, and also the dynamic viscosity is 03073. Alright, well done. Marah pula ABC punya. Abang penyu. Tak apa-apa, kita teruskan. Okay, so now we have the density and also viscosity. So where do we go from there? We need to find the V average, because we need to find the Reynolds number. Remember Reynolds number? V average diameter over viscosity. So we need to find V average. V average. Okay. So this is the velocity profile in a fully developed laminar flow. Okay, since dia dah cakap sini laminar, so automatically we are using the laminar equations. Okay, where do they find this? They find it over here. Laminar flow, velocity profile. Sini dia guna velocity profile ni. Okay. So velocity profile, basically we can just skip here. Vmax over 2 equals 3. Okay. Average velocity for fully developed laminar flow. Okay, so now we already have the V average. Now we can find the Reynolds number. Yes, Reynolds number. So we key in the density, the velocity, the diameter, and also the viscosity. You will get 488.9. Where's my calculator? Okay ni. Okay, guys, guna calculator. Kena guna calculator walaupun ada jawapan kat situ. Okay, 1252 times 3 times 0.04 bagi 0.3073, 488.903. Okay, so this is less than 2300, so it is confirmed to be laminar. Okay, so from that we want to find the friction factor. So since it is laminar, we use this friction factor. F equals to 64 over RE. F equals to 64. So we will get 0.1309. Okay, that is our friction factor. So now we want to calculate the head loss. Head loss, mana? Ni head loss. Head loss equals to pressure drop over rho G, which is also equals to F LD V2 square average over 2G. Kita dah jumpa V average, kita dah jumpa F, L kita dah ada, D pun dah ada. So kita tinggal masukkan saja. Okay, let's do this. 0.1309 times 70 times 3 squared over 0.04. You guys kena buat sama-sama tau. 2 kali 9.1. Tak tahu kalau nampak kita. Dia dapat 105.08 meter. So that is our head loss. So dia tanya, velocity profile dah jumpa, pressure difference belum jumpa lagi, but kita dah jumpa head loss. So from the head loss kita boleh cari kita punya pressure difference. Mana? Ada pressure difference. So mana? Ni kan head loss kan. Head loss equals to pressure difference over rho G. So nak cari pressure difference, taruhlah dengan rho G. Okay, so kita punya HL 1.9 tadi darablah dengan mana kita bagi 1252 darabkan dengan 9.81, dapatlah 1290.6 kilopascal. So this is pressure drop. Okay. So kita boleh guna lagi satu cara, which is using the energy balance. Energy balance ni. Energy balance ni. Tapi sebab kita dah ada simplified punya ni, kita guna 3. Okay. So dapat sama juga 120.6. Okay. Okay, so far so good. Kita kena cari Reynolds number, friction factor, head loss, pressure drop. Okay. Benda tu kena ingat. So kita tanya soalan apa ni? Pumping power. So pumping power tu is the pressure drop lah kan? Okay. So this is the pressure drop. This is the, okay, so we need to find flow rate. How do we find flow rate? Flow rate is V average times the cross-sectional area. So this is our flow rate, 3.77. Okay. So pumping power is, okay, flow rate is what? Volume over seconds times pressure. Pressure is force over area. Volume is meter cube over S times over area pressure Newton. Mass L equals 2 over T equals 2, L equals 2. Cancel. So dapatlah M equals 4 over ST. So ST square equals 4. Ya Allah, L equals 4, bukan L equals 4. L equals 4. 3M over ST. Okay. So that is kilowatt. Okay. So sekarang ni tanya, what is the flow rate, percent increase if the theta is 15. So right now we want to see the difference in elevation. Okay, remember the total head loss is equals to the difference in elevation tambah dengan head loss from mana kita belajar ni? Ni H pump. Remember this? Pump. Okay. H pump equals to difference in elevation plus the total head loss, which is Z2 minus Z1 plus HL. Okay, so apa ni? Okay, ni pressure drop plus okay, so korang perasan tak? Okay, let's just do another equation. Okay, from here we see that 15. Okay, L is equal to 70, theta is equal to 15. So the vertical length would be 70 times sine 15. Okay, masukkan dalam calculator, korang akan dapat 18.1173. So that is the vertical distance or the difference of in elevation. Head loss mana tadi? Head loss. Ni head loss kita 105.08. 105.08 tambahlah, tambah 105.08 123.197. Ni H pump. Kita nak cari pressure daripada H darabkan dengan rho G. Okay. Okay, so nampak ni. Satu tak nampak tu. 123.197 darabkanlah dengan rho dia, which is 123.197 darab 1252 darab 9.81. Dapat jawapan ni. Dapat dah. Dah senang. H pump darab H pump darabkan dengan rho G, kau akan dapat pressure drop. Okay, so daripada pressure drop tu boleh cari flow rate sebab kita punya pumping power constant. Pumping power kita daripada mana? Daripada sini. Pumping power kita bagi. Okay, so ni kilowatt. Ni kilowatt, ini kilopascal. So 10 kuasa 3 tu cancel out each other. So korang akan dapat 4.866 bagi 1.12.9. Korang akan dapat 3.216 darab 10 kuasa negatif 3 meter per second. So this is the flow rate. This is the flow rate. So the difference, percentage difference ni, the initial or the bigger one bigger minus smaller over the bigger. So you guys akan perasan dia akan decrease. So same goes to here. Cari H pump, which is equals to Z2 minus Z1 plus HL. Pressure difference equals to the H pump darabkan dengan rho G. So kau akan dapat 106.8.3. Sebab ni dia negatif, sebab kat sini negatif. So the head loss is actually head increase, because if you going down a pipe, you can gain potential energy. So the flow rate increase, so that makes sense lah. Ni untuk cari, we can also use Hozier's law. Tadi kan kita just use this formula kan. Boleh guna Hozier's law juga. Hozier's law sini. Cuba korang try masukkan pressure drop tadi. Kita copy je. Ni copy, delete. Dah ada dah sini. Ya Allah, terpaksa. So korang masukkan pressure loss dia. Dapat tak flow rate ni? Kita try buat yang 106.8. 106.8.3 minus Rho GL sin 15. Ni negatif 15 ni, so dia ditambah pi 0.0404 bagikan dengan 128 mu dia, mu darab L. Okey, 1068.3 tambah 1 kat sini 1068.3 tambah rho dia 1252 9.81 rho G apa? Sin negatif sin. Sin 15. Korang kena buat sin 15 pi 0.04 pi 0.0404 bagikan dengan 128. Viscosity dia 0.73. 0.73 L 70. Ini kilo Pascal ni, ini darab 10 kuasa 3. Okey, kita try darab 10 kuasa 3 tambah 1 darabnya darab 9.1 darab sin 12 tambah pi darab 0.04 bagi 128 darab 0.3073 darab 70. 3/12 berapa? Something 3. Okay, so dapat 3/7. Okay, so that is for question 1. Ada question for question 1? Any question? Ada. Kalau tak ada, kita buat question 4 ke nak lihat ada tepu dulu. Kau nak tepu tepu gila mat. Nampak dah ni lagi. Nope. Okay, so boleh move on next question. Try question bawah tu. Okay, yang tank. Oh, yang tank ni untuk bagi dulu. Okay, is to be filled with oil. Okay, vented tank. Vented among us. Vented means pressure equals to 1 atm. Okay, rho equals to 920. kg over mg rho is equals to 0.045 kg m dot s from underground reservoir origin. L equals to 20 meter, D equals to 0.05 meter with slightly rounded entrance. Slightly rounded entrance means into 90 degrees movement. Okay, so this smooth entrance, also 90 degree smooth bend. The elevation difference between the oil level and the reservoir of the top tank where the hose is discharged is 5 meter. Delta Z is equal to 5 meter. The capacity of the tanker is 18 meter cube and velocity volume max 18 meter cube, and the filling time is 30 minutes. Equals to 30 minutes. Taking the kinetic energy correction vector at hose discharge to be 0.05. Okay. Alpha equals to 1.05 for the kinetic energy correction hose discharge. This is the discharge. Assuming an overall pump efficiency of 82%, determine the required power input to the pump. Pump motor equals to 82%. Determine the required power input to the pump. Required power input. Okay, so let's see. First, kita tengok sama ada dia turbulent ataupun dia laminar. So let's find the Reynolds number. Is equals to rho V average D over V average D viscosity. Okay, we don't know what is V average, but we do know is the mass flow rate, which is 18 meter cube over 30 minutes. 30 minutes also equal to 60 seconds. So 18 over 1800, 0.01 meter cube per second. Am I correct? Hello, are you there? So this is the flow rate. Okay, so what do we do? Maybe it can become turbulent, maybe it can become laminar. We don't know. But what we do know, it has a pump. Okay. This one, conservation of energy. Okay, let's write the conservation of energy. Great. V V1 over V2. Okay. let's put our assumption first. Assumption first one to be flow is fully developed. Flow is incompressible, steady. Okay, so mass flow in equals to mass flow out because there's only one pathway. So there will be equals to AC. So since the this is the same, it's the same. So velocity in is equal to velocity out. So what is the velocity? Velocity is equals to AC V average. So pi pi b squared pi r squared times V average. Kita nak cari V average. Kita dah ada place for it. V V average equals to V dot over AC 0.01 over pi r squared 0.01. Okay, pi darab 0.025 squared 0.2 so dapat jawapan 5.093 meter per second. This is our V average. So now we can find our Reynolds number. RE is equals to the viscosity, the V is 920. The V average is 5.093. The D is 0.05 over the viscosity is 0.045. 0.045. Okay, so let's calculate that. $5206.1778. Okay guys, so from here we know that the Reynolds number is bigger than 4000. So it is turbulent. Oh my god, it is turbulent. Okay, so if it's turbulent, we want to find the friction factor. Why do we want to find the friction factor? Because we want to find head loss. Head loss for turbulent is kita guna ni FLD V square bridge. Okay, FLD times V average h squared over root 2g. Find f. We use Darcy friction factor, which is f equals to, oh, we cannot use that. We don't know the shear force. So what we do is we use Colebrook equation ataupun explicit Allen equation. Let's use, okay, is it smooth pipe, guys? Does it say it is a smooth pipe? Plastic hose. Plastic is smooth. Betul, betul, betul. Plastic is smooth. Even if we rujuk here. Plastic is smooth. So we use Prandtl equation. Oh, thank God we're using that equation. Cannot. We don't know dw. So now use Prandtl equation because smooth. Why smooth? Because epsilon equal to 0. Okay, so what is the equation? 1 1 over square root of f equals to 2 ln REF third minus 8 minus 8. Okay, so we know that 2 ln berapa ni? 5,000 5,200 berapa? 5,200 5,200 F minus 8. So kita cari sini 1 over square root x equals to 2 ln square root x minus 8. F kita akan dapat 0.013. Okay, this is the first solution. Second solution is using Moody chart. So let's see the Moody chart. Where is the Moody chart? Okay, so kita punya go equal to 0 kan, smooth pipe kan. Smooth pipe kita sini. Dan kita punya tu pun 5,000 kan. Sini 5,000. Somewhere over here lah, somewhere over here. Okay, so apa yang nak dapat? Tapi nampak 0.03 lah. So supposedly 0.03 something. 1.3 1. Okay. Oh, satisfying juga dapat ni jawapan ni. Okay, so you guys dapat jawapan tak? Dapat F tak? Dapat F tak? Masih hidup ke? Betul tak hilangkan set F tu macam mana? Okay, aku guna calculator ni lah. So kalau guna calculator ni, kau boleh buat macam for JJ lah. Kau boleh buat macam write the whole equation tu balik. Just write the whole equation tu balik. Lepas tu tekan equals tu. Tapi guna alpha guna yang calculator putih ni. Tahu lah macam mana cerita. Tapi aku guna cara ni lah, dapat 0.031 something like that. Aku key in terus dalam iPad, terus dalam calculator. So akan dapat ni. Okay, so using Moody chart for verification. So we're on the right track lah, 0.03 something. Okay, so now dah jumpa tu, we need to find head loss. Okay, head loss, oh my god, head loss is equals to F L over D times V squared over 2G. Dah jumpa F, dah jumpa L. Okay, semua dah jumpa. 0.0313. L is 20. Diameter is 0.05 times V squared is 5.093 squared over 29.81. Ada cara lain untuk solve equation selain daripada equation solver? Don't know. I don't know. Because I'm not good at this. Yeah. Tambah 8 equals to 2 log 5 206.178 F. So 2 bawa di sini, dapatlah 1/2 F tambah 4 log 5206.178 4. Okay, so log sama dengan E kuasa 1/2 F tambah 4 sama dengan 5206.178 punca kuasa F. So dari situ ke? Saya rasa I don't know. Lepas tu dari sini dia masukkan lah. But basically I just use my calculator. So I'm very sorry, but use the white calculator. Okay, so now we resume here. Okay, so berapa kita dapat? 0.0313 darab 20 bagi 0.05 darab 5.093 square over 2 darab 9.1. Kita dapat 16.55208 meter. Okay, you guys dapat tak this one? HL, dapat tak HL? Tak tahu tak apa. Okay, so sebabkan dia kata dia ada minor losses, so we need to add the minor losses. So this is what we call major loss. Now we need to calculate the minor loss. Since we have two entrance, our slightly rounded entrance and 290. We have one entrance and two band. So now kita tengok macam mana ada ni KL equals to alpha. Kinetic energy correction is fully developed turbulent flow. See, it's turbulent. Kita on the right track. Oh, okay, so from here we know that the entrance is KL equals to alpha, which is equals to 1.05. What about the bend? How about the bend? Is it flange or is it threaded? I think it's threaded. 0.9. KL equals to 0.9. Ada dua. Tengok dua. So total KL is equals to 0.9 times 2 plus 1.05 equals to 2.85. Betul. Okay, betul. How do we know if it's threaded or not threaded? Because kat sini dia tak tunjuk apa. Okay, tak apalah. Kita tuliskanlah. Okay. So remember this minor losses. Okay. So mana minor losses? Ni dia minor losses. Apa beza flange and threaded? Okay. Flange is something like this. Threaded is that. Okay, let's just go. Is it flange or is it threaded? Okay, let's just read this properly. I think it's threaded because it's plastic. Because if it's besi, it will be flange. If it's plastic, it will be threaded. So let's put an assumption here. Assuming threaded bands, because use plastic pipes. If it was metal, it would be flanged. Okay, is that clear with everyone? Okay, HL equals to FL over D plus total K darab V2 kuasa G kan, 2G. Okay, sebab apa? Why we use this is because the constant diameter from where? From here. See this one? This equation? So I think you can rewrite the equation. 0.0313 L is 20 over 0.05 plus apa ni? 2.85 5.0 berapa tadi? dia velocity dia 5.93 over 2g square. Okay, cuba you guys kira. Boleh guna calculator equation method untuk solve equation for questions in example. Boleh? Boleh. 0.0313 darab 20 over 0.05 tambah 2.45. So akan dapat 15.37 5093 squared over 2 times 9.1 akan dapat 5093 squared over 20.332 meter total HL. Okay guys, now we already found the total head loss, which is 20.32 meters. So now we do the conservation of energy. P1 over G rho G plus G again. This one. You guys kena ingat ini formula plus V2 over 2G plus H Z1 H bar Z1 equals to P2 rho G plus V2 squared over 2G plus Z2 plus HL plus H pump, H turbine. Okay, now we want to cancel out. Okay, so as we see here, it is a vented tanker. It means that the P1 is equal to P2. So there would be no difference in the pressure. Okay, the plus HL, the minus Z1 is another thing 5 meter. Almost there. Plus HL. Berapa tadi? 20.32 meter. Dapatlah 25.32 meter. Betul? Betul. H bar. So pressure difference. Okay. What is the pressure difference? Pressure difference is H bar darab 2G. 25.32 darablah dengan what is that bro? 920 9.81 25.32 times 920 times 9.81. You will get 228.52 kilopascal. The power is times flow rate. Betul? Betul. The flow rate is 0.001. So 228.52 kilopascal times 0.01 meter cube per second. betul. 0.01. So dapatlah W is equals to 2.285 kilowatt. But there is a but. There is the required input and 82% pump efficiency. So pump efficiency is equals to input here input required up to 2.285 over input equals to 82%. So input is equals to 2.285 bahagi 82, 0.8. 2786. Oh ya, start jap. Ulap. Oh, dia overheat ke? Rasa dia overheat. Jap, apa dia ni? Dia cabut. Dia cabut. Okay, so final answer aku dapat ni tu. Mn equals to 2.28 apa ni? 2.2852 kilowatt over input 0.82 input equals to 2.786 kilowatt. Ini final answer aku. Tu je ke? So boleh ke guys? Korang dapat tak jawapan ni? Are you guys still there? Oh, 4 viewers. Kenapa begitu? Tengok kau dapat lah. Maksudnya okay. So do you guys want me to share this or it's a very bad Android but I think you can dapat lah. So apa tak aku buat ni? Cari Reynolds Number. cari ni, lepas tu cari head loss 3, lepas tu cari minor loss 4, lepas tu letak dalam ni 5, 6, 7. There were 7 steps. So this is it. Okay, so I think that is all for tonight. You guys ada questions ke? Macam mana nak tahu dia kena cari minor loss ke tak Because dia cakap question yang ada bending and also apa entrance region tu. So automatically dia consider the minor losses. And then dia tengok ni, one thing you need to know is that dia ada mention pasal kinetic energy correction factor. That only occurs when there is this ini yang A ni, A kecil ni. So kau kena guna equation ni. Okay, ada juga kan discharge. Okay ke semua? Ni discharge coefficient. Okay, see you guys tomorrow. Team France. Okay, thank you so much guys. I am very proud of you for the one sticking at the end. Give yourself applause. Round of applause. Well done JJ, well done Aiman Nasuha. Thank you, welcome. Okay. Bye bye guys. Bye bye. That will be the end of our stream. Welcome JJ. Bye bye.